welcome to our physical sciences session. My name is Temba Ngube. Today we are looking into electrostatics. The major theme for today is investigating charges. We want to find out exactly how charges interact with each other in space and how does charge arise in nature, and try to bring on some kind of some understanding of sort in terms of thinking what we already know to how point charges interact with each other in space. So our theme for today is investigating charges. Now let's look at a big question for today. Have you ever thought about how objects become charged in nature? The idea of making everyday life observation in as far as static electricity. It's one of the obvious things that happens around us, because the science that we do in class is actually very much alive around us, right? So let's look at the concept map or the mind map in as far as the charged objects are concerned. We have managed to look in the past at properties of materials physically. That is, we can talk of conductors as materials that allows charge to pass through them, while insulators, they do the opposite, or they exclude charge. So these are different materials in real life, right? So as far as the physical properties, this would lead us to understand how charge arises, or how objects in real life, they become charged, right? Okay. Now, having said that, any object consists of atoms as the building blocks of all matter as we know it from earlier grades. Now, we are saying that these atoms, they consist of subatomic particles. Now, the subatomic particles that we talk of are obviously your electrons, your protons, your neutrons. And already in these three subatomic particles, we've got positive charges as well as negative charges. This is the main focus. But now, if you go back to the electronic structure, or the atomic theory as we know it from the previous studies that we've done, would also appreciate that these electrons occupy what we call the energy levels, or the shells. Sometimes we call them the orbitals. Now, the transfer of charges occur, or the occurrence of a charge is a result of materials either losing electrons or gaining electrons. Let's look deeper into the dynamics of that. Okay, so if we have an object that is neutral, neutral suggests that there's an equal number of protons. Protons are positive subatomic particles, while electrons are negative. So if the number of protons and electrons are equal, then that material or that object becomes neutral. Okay, right. Now, if we bring a charged material closer to a neutral, as we'll demonstrate during the course of our session today, there's something that is called polarization of charge, where by the electrons shift. Why is it about the electrons? We've already mentioned that electrons are actually the ones that are transferred between materials, and we are saying that if a material is polarized, it means one end of that material becomes more positive, okay, while the opposite end becomes more negative. Now, still, in essence, we still maintain that the number of positive as well as negative charges is still the same. Hence, it is neutral. But polarization has to do with, having two ends of the same material having opposite charge, one becoming positive and the other one becoming negative. We shall talk to that as we go along. All right. Okay. Moving along, and then what if a material that's neutral gains electrons? What happens to it? Okay, it becomes negatively charged. So in essence, if we're saying that this material is negatively charged, what do we mean? Does it mean it doesn't have positive charges? Definitely not. It certainly says to us that the number of negative charges contained in this material is comparatively higher than the number of positive. Hence, the net charge becomes negative. So that's the nature of charge as a specific example. All right. And then moving along again, we can have a case whereby electrons are lost. Remember, you'd also realize that it's either gain of electrons or loss of electrons. It is about the electrons, all right? And then if electrons are lost, that material becomes positively charged, okay? What does it mean? it means that the electrons have been lost, meaning by implication that the number of positive charge now is comparatively greater than those of the electrons. Hence, the net charge that material has becomes positive. So it's actually the opposite. So we do not necessarily add positive charges to a material for it to become positively charged. What essentially happens is that it loses electrons, because these electrons are exactly what we have in terms of negative charges. All right, okay. Right, moving along, now we would get to a point where we have got a positive and a negative charge, and these are opposite charges. Unlike charges, we know there are forces that exist between them. So that's the big idea in as far as the origin of charge is concerned. Now, the force is in terms of the negative attracts the positive and the positive attracts the negative. We shall talk to that at a later stage, right? Okay, now, and as far as the concept map, we want to look at the forces involved when objects are charged, right? Now, we have two point charges. We can have this one, we'll call it B for now. The other charged object, we'll call it C. And we can immediately assume, okay, we've used the color code there just to say that the type of charge that C has is different from B, whatever the case may be, all right? And then there is a force that B exerts on A, and there's a force on C rather, and there's a force exerted by charged object C on B. Now, this is a force of attraction. If you go back, I think at a very basic elementary level, you'd understand that a force is either a push or a pull. That's how we defined it at primary. So what do we mean if we're saying a force is a pull or a push? We are saying that a particular object exerts a force on another. That force could actually be pulling that charged object toward itself or actually pushing it away. So in both cases, there is a force that exists between any 2 point charges in space. All right, okay, so there is a force of attraction. So we've got the force by C on B, all right? There's a force by C on B, and then we also have a force by B on C. So these are two vectors. So we'll talk about vectors at a later stage again, right? And then if we also look at, if we say, for argument's sake, we've got three now charged objects. In this case, we've got B, C, and A, right? Now you'd realize that A and B and C are opposite, while A and B are like charges. So if we consider, say for argument's sake, the force exerted by B on C, let's concentrate on C. So there are two objects that exist that exert an electrostatic force on object C. So if we were to draw a vector diagram or a free body diagram, we would have something of this sort. Now, the force on C by B is actually in that direction, because these two are unlike charges. So this is force by B on C, right? And then if, again, we look at the force by A on C, the direction of that force is towards A, because these two are oppositely charged. So this is the force by A on C. So this vector diagram actually is a representation of the vectors or the forces that act on object C. Now, why do we have two forces in this case? You'd realize there are two objects that exert simultaneously a force on object C, right? When that happens, then we would know that, okay, there will be also, equivalently, there will be also two forces, right? Now, if you think about the net force that acts on C, due to both B and A, it will be in that direction. So this is our F resultant or our F net. So this is the charges and forces as they exist in nature, all right? Okay, so there is an attraction force. We've already looked at that. So that's the direction of the net force as you would have it in that way, right? And then we can play around and change. Okay, now these two are actually like charges. We have got C that has got a similar charge to D. But as we know it again, like charges, they exert a force of repulsion on each other, while opposite or unlike charges exert a force of attraction. So attraction is pulling together, repulsion pushing away. So that's as simple as we can break it down. Right, so if we consider object C once again and look at the forces that act on object C due to object B and D, right, what is actually happening? If these two are attracting each other, we will have a scenario where the force exerted by B on C is still in that direction. Nothing has changed. Force by B on C, right? While on the other hand, charge C and D are like. What's going to happen? D is actually going to repel C away from it. So this is the force on C by D, right? So this is force by D rather on C, okay? So we're looking at C as our object of interest. Now, what would be that we can, at this point in time, we are able to predict the direction of the net force. So this will be the F net on C by B and D. So this is our F net or our F resultant, okay? So actually it will show it, there it goes. So this is our net force, okay? Right, right. And then in as far as the big idea, we've managed to look at conductors as materials that transfer charge, that allow charge to move them through them, while insulators, they exclude. We've also managed to talk about the origin of charge in terms of gain, okay, and loss or loss of electrons. It can be one of the two, okay? It's not both at the same time, okay? We've also managed to look at the vectors in terms of the forces that exist between any point charges in space, right? So having said that, we also managed to look at the very important keywords. Charge is a property of matter, right? So charge is actually a property of matter such that it would experience an electrostatic force when it interacts with another charge. So we talk of either, this can either be what? Positive or negative. And what do we mean by that? It can only be positive if electrons were removed from a material, and then the quantity of charge that material will carry will be positive. While if the opposite happens, when electrons are added to it, that charge will be negative. So that has to do with the nature of charge. Now, we can talk of identical spheres. Now, this is the real concept in as far as, the charge in real life. So when you talk about spheres, you remember the charge accumulates on the surface of the sphere, all right? So if we say two spheres are identical, exactly what do we mean? We are saying that these materials are of the same shape, size, color, in whatever respect, everything is the same. However, it does not necessarily mean that they carry the same amount of charge, unless, of course, it says identical charges. So pay careful attention to the language, because every scenario is unique in its own way, okay? So the word identical suggests that they are maybe of the same shape, color, but it may not necessarily mean they carry the same amount of charge, except when the statement says identical charges. So you must be in a position to distinguish between identical spheres and identical charges. When it says identical charges, it means Q1 is equals to Q2. What that simply means is, let's say, for example, Q1 is 5 nanocoulombs, and then Q2 will also be what? 5 nanocoulombs. Then these two are identical charges. But these identical charges may necessarily be on a insulated stand, okay? So let's say that's plus 5 nanocoulombs, okay? That's our Q1, okay? So if we say this is an insulated stand, already we are talking about the physical properties of materials. We're saying that the only amount of charge that we have here is plus 5 nanocoulombs, which is carried by this sphere Q1. And then if we say, for argument's sake, we've got another one, we call it Q2, okay? And then this Q2, let's say it's negative 5 nanocoulombs. What does that mean? It means that on this sphere, there is an excess of negative charges, which are the electrons, whose magnitude is negative 5 nanocoulombs. What does that mean? It says that electrons were added to Q2 to create this charge Q2, while electrons were removed from Q1 to create that charge of positive 5 nanocoulombs. So if we talk of the isolated, the term isolated or closed system will come up once too often in our discussions that will follow. Be aware that when we talk of an isolated system, we are talking about a system where the net or the total charge in that particular scenario or system remains the same. We shall talk to that at a later stage. And then the last term that is very key in as far as charges is earthing. You know, when you talk about the earth, you know, nature always makes an effort, you know, to restore balance in its own way. That's what it happens. So if there is an accumulation of charge, naturally what will happen, all those charges will be transferred to the ground, hence the earth wire, you know, in our everyday lives. So those are some of the legal terms that are very important in as far as the terminology is concerned. Now, in the next segment, we shall delve deeper into more details. But for now, let's take a short breather. Welcome back to our second segment. Now we focus our attention on, you know, the real life, you know, applications of electrostatics, you know. And remember, in science, we so much talk about predictions, you know, quite a lot to say, okay, what would happen if you take a balloon, you know, and rub it on your jersey, woolen jersey, you know, already we are thinking the science behind that demonstration to say, okay, there is friction while the two surfaces are actually in contact. So there's a force that, you know, the balloon exerts on the jersey, and while that is happening, our focus or our concern or what is of interest to us is exactly what happens to the charges, you know. While they come into contact, charges will actually be transferred. Now let's look at a scenario where you rub a balloon on a woolen jersey. Take note of the material. A balloon is rubber, okay? This is rubber, right? Okay, and then a woolen jersey, it's a different material altogether. But both of them are actually, you know, different types of material. And so one of the two is actually an electrical conductor. So rubber is an insulator, right? So the rubber is an insulator, all right? And then the woolen jersey is actually an electrical conductor, all right? So if these two are actually rubbed against each other, we've got a scenario here that I just want us to look at. Okay, here's a typical example of a balloon, okay? Now, what is happening? The balloon is neutral. Now, let's break it down. When a material is neutral, does it necessarily mean that it doesn't have any charges? Definitely not. It says the number of positive charges equals the number of negative charges. Hence, the net charge is equals to 0. Okay, so neutral materials do retain charge. However, the amount of charges, positive versus negative, is equal. Hence, the net charge is equals to 0. That's the most important thing. Now, if you look at the balloon in itself, the number of positive charges in this simulation of the balloon, it is the same as that of the positive charges. The similar thing can happen with your woolen jersey, right? So the woolen jersey has got a lot of atoms, millions and millions of them. Now, the number of positives, again, is equals to number of negatives. So what happens if we rub these two against each other? Just look at that, okay? Look at the changes that have happened. And look at, observe the force that the jersey exerts on the balloon and vice versa. Now, if we pull this balloon away and try to analyze it, there are some observations that we've definitely made there. You'd realize that now there are many negative charges on the surface of the balloon than it initially was. So what that says to us is that the insulator, sorry, the conducting material, which is the jersey, had, you know, some of its negative charges transferred to the balloon. Now, you can immediately predict that, oh, okay, now the balloon has more negative charges than positive, meaning that the net charge on the balloon is actually negative, while the opposite is true for the jersey. On the surface of the jersey, closer to the balloon, you'll see that there is a cloud of, positive charges. Now, yes, charge, if they come into contact, the transfer does okay. But if we bring them closer, what exactly happens? We still have more and more charges getting to the balloon, and you can immediately, if we pull it away, naturally, this balloon will move towards the jersey, as you can see. It's magic, but yes, it's the science which explains how charges or charged materials interact with each other. Now, beyond just the transfer of charges, you also need to recognize and appreciate the fact that, there are electrostatic forces that exist between the balloon and the jersey. Now, the force exerted by the balloon on the jersey, because on this side, they're actually positive and negative, which is oppositely charged. There's an attractive force, which explains then our everyday life observation. You take off your jersey, you are rubbing the jersey against your body on a hot summer day. You observe some sound, some sparks. So that's static electricity. It's a perfect example of exactly what happens when two materials are rubbed against each other and charge is transferred between the two of them. But what is of also particular interest to us is the nature of charge that arises due to friction while you rub them, as well as how these charges end up interacting with each other. What we already know is that positive and positive, they repel, while positive and negative, they attract, which is the case with the balloon and the jersey. So that's quite an interesting observation. Right, moving along, right, we would also want to look at a scenario whereby the very same balloon and jersey is actually between two materials. That's your wall over there, as well as that's your jersey. But now we've resetted everything. Let's go back to the simulation and talk to it a little bit. Right, now I'm gonna reset everything, but now you'd realize that we've got a wall. Okay, the wall is also neutral, right? Because in parties, balloons are a very common feature, and some of these demonstrations, I think they'll bring an understanding of, the science behind, the everyday life observations that we make. So if we take the balloon to the wall, you'll realize that there's not much happening there. Why? Because both of them are actually neutral, and both of them are actually insulators. Now, the charge cannot be transferred between those two. However, if we do the opposite, you go to the jersey, that there is that observation. Now, look at what happens. Now the balloon can stick onto the wall, okay, because it has acquired excess negative charge. It means it has got more negative charges than positive charges. Hence, the net charge in it is actually negative, right? Okay. So that was the simulation. So the science actually behind the everyday life observation is what is of interest to us today, to say there is some thinking as to why we see or why we observe what we do in everyday life. It's static charges, interacting with each other in real life or in space. All right, okay? Right, then another prediction, when you bring a charged comb, okay, you can try this at home. You are free to do that. You can bring a charged comb. Now the comb is charged already. Now let's unpack the charging of the comb. Ask yourself the important question: how do you charge a material? It's either you rub it against your hair, or you rub it against your jersey, or whatever material. What will happen is that this material will either acquire excess charges or have more negative charges or more electrons than protons, or it will lose electrons. Whichever way, it becomes charged. Whether it's positive or negative, it's a material for now, right? So if the comb is charged, and then we bring it closer to a stream of water. This is the demonstration that I'm talking about. You'd have observed this maybe at home. You'd realize that the stream of water bends. Now, what does that say to us is that there is a force that exists between the comb and the water. Water in its very nature, it's polar. We've spoken about polarized. It means the water molecules, the water molecule actually has a side which is positive and the side which is negative, right? Something like that. So what that simply means, water is polarized. Yes, it's neutral, but the distribution of the charges in the water molecule is such that one side of it is positive and one side is negative. So when you bring a charged comb, let's say this comb is positively charged, what will happen? The negative side of the water will actually be attracted to the comb. This is one classic example of how charges interact with each other. It still goes back again to say that like will repel and opposite will actually attract, right? Okay, and then how can you detect if something is charged or neutral? There is a piece of apparatus in science that we refer to as a gold leaf electroscope. So what it does, it actually demonstrates the interaction of different types of charge, positive and positive, repelling each other. The similar thing happens with like charges which are negative, while the opposite, which is the positive and the negative, actually exert a force of attraction on each other, right? Okay, so here is a scenario. So say for argument's sake, we've got a material that is charged. This is negatively charged. The electroscope is neutral. Let's put it out there to say that if this is the the simplest grammatic representation of what an electroscope it looks like. Okay, so if we bring this closer to the neutral electroscope without touching, polarization does occur, okay? Right? There is polarization. Remember, if we don't make contact, the field forces or the non-contact forces happen, actually act on these charges. And polarization is due to non-contact forces, all right? Okay, so non-contact, it means the two materials must not be in contact with each other for them to actually exert a force on each other, okay? So if we bring this, what is going to happen? The positive will actually be repelled, which brings us to repelling the negatives have been repelled because the material in itself is negatively charged. So once that happens, if we polarize the negative by repulsion, without even making contact with that part of the electroscope, these two leaves will actually deflate because both of them will be more negative. So what do we know about negative charges? They experience a force of repulsion. Hence, we say that the leaves will deflate, okay? Similarly, if this was, let's say for argument's sake, positive, what would mean? It will also polarize the positive charge by reflection, by repulsion, and then what happens is a similar observation will be made because this will be more positive. So in other words, we are saying that the interaction of charges is in nature is actually twofold. Well, it will depend on the nature of charges under consideration. If these two charges are alike, then we are saying that a repulsive force will exist between them, while if they're opposite or unlike, an attractive force will exist between them. So that's the gist of our discussion. Having said that, I think we'll take a short breather and then we'll look at quantization of charge. Exactly what do we mean when we say that charge is quantized? Let's take a short breather for now. Welcome to the third and final segment of our Investigating Charges session on electrostatics. Now we want to look at what exactly it means, when we say that charge is quantized. We've already, just to take you back from the first segment, we say that the subatomic particles, which are electrons and protons, are exactly what contributes to the type or nature of a charge that a material has. Right. Now, having said that, so we want to focus on what we refer to as quantization of charge. Let's start that with a discussion which says that two charged objects are attracted to each other and touch. Predict what happens next. Right. Now, we've got two objects, all right? Let's call this one Q1, okay? Let's call this one Q2, right? Now, already they're at a distance apart. It means that Q1 exerts an electrostatic force on Q2 and vice versa. right? But now you must also think about the forces in terms of the vectors. The force by Q1 on Q2 is actually towards Q1, while the force on Q2 by Q1 is actually in the other direction. So the direction in terms of vectors is very important. Now, if we bring them into contact, okay, what exactly happens? Charge is going to be distributed. So touching is actually a physical process, right? Okay, so touching is actually an example of what we call a physical process. What do we mean? They come into contact with each other. And as long as these two materials are conductors, right? So conductors, remember physical properties, are materials that actually allow charge to move or to be transferred between those materials. So we refer to them as the conductors. So this one is plus 2 nanocoulombs, and this other one is negative 5 nanocoulombs. Now, in terms of measurement, in terms of magnitude of quantities, in science, units are a very important or critical component, because when we do problem solving or calculations, that is, we need to pay careful attention to the SI unit. So the conversions are very important. Just to get that out of the way, we know that for argument's sake, when we have got 1 millicoulomb, for argument's sake, this is equals to 1 times 10 exponent negative 3 coulombs. So this is like 1,000th of a coulomb. While we have got 1 microcoulomb, this is 1 times 10 exponent negative 6 coulomb. This is like a millionth of a coulomb. It's a fraction. So these are smaller units. And then we get to the nanocoulomb. 1 nanocoulomb is equals to 1 times 10 exponent negative 9 coulomb. And then we usually also deal with picocoulombs, which is 1 times 10 exponent negative 12 coulombs. So this should be very clear from the onset in terms of units. Right. And then now if the two come into contact, that's the physical processes, we know that electrons are transferred. Right. Let's break it down. What exactly do we mean when we say electrons are transferred? If we have got Q1 and Q2, if Q1, for argument's sake, loses, okay, whatever is lost by Q1 equals what is gained by Q2, all right? So what is lost is equals to what is gained is also equals to what is actually transferred during that contact or the physical properties that we earlier referred to, right? So the transfer of electrons occurs. But here, it's very important, if we can quickly go back to that, Q1 is positive. What does it mean? Q1 has more protons. This one has got excess protons, right? Okay, so this one has got excess protons than electrons, while Q2 has got excess electrons. Just take that into consideration. So meaning that for Q2, there are more electrons than protons, right? Okay, having said that, so the Q2 is more negative, while Q1 is more positive. So this one is more negative, okay, more negative, while Q1 is more positive, right? So if the transfer of electrons occurs, it is actually from Q2 to Q1, right? This is what we mean when we say electrons are transferred. But also let's take into account that the transfer is actually from Q2 to Q1, okay, in that order, as the arrow suggests, right? And then once these two are actually in contact with each other, charge will be equally distributed. So we've got what we call the net charge, which is the Q net. So the word net is very, very important in physics, because we are going to use this word many instances when we talk about the net force. We've spoken about the net electrostatic force, for argument's sake, when we started our first segment. But now we're talking about the net charge. Now, the net charge is the total. So the word total is in other words, would say net or resultant. But in this case, we're talking about the total charge, which is Q1 plus Q2, right? Q1 plus Q2, that's our net charge, meaning that this is, if we can go back quickly, just to verify that Q1 is positive 2 nanocoulombs, and the other one is negative 5 nanocoulombs, right? So if we talk about the net charge, is 2 nanocoulombs, which is positive, plus negative 5 nanocoulombs. So the net charge in this system therefore becomes a negative 3 nanocoulombs, right? Now you'd realize that after the charge has been equally distributed due to the contact, what exactly happens? Still, after contact, after this physical process, Q net is still negative 3 nanocoulombs, which is from negative 1.5 plus negative 1.5 nanocoulombs. And then I want also to draw your attention to the nature of the force that exists between them. Initially, they were oppositely charged, then they were attracting each other. While they've got the same amount of charge, now after the charge has been distributed, they experience a force of repulsion because now they are like charges, both of them are negative. Now, the new charge that each one of them attains as a result of the contact process, of the process of coming together into contact, which is a physical process, we're saying it's equals to Q net, which is the total, divided by 2. Why do we divide by 2? It's because this charge is equally distributed. Then we'll get negative 3 nanocoulombs divided by 2. Then the new charge in each one of them, which is the same for both, is actually equals to negative 1.5 nanocoulombs, which is exactly that, right? So that's the thinking. So when two materials are brought into contact, charge is equally distributed, but we must also note that the net charge before they brought into contact and separate is equals to the net charge even after they were separated from each other, right? Okay, so what charge was transferred? Okay, now we're talking about the charge which was transferred. Now, the main thing here is we need to arrive at a point where we are able to say, okay, indeed, charge is quantized in terms of the electrons that are lost by, Q2, which is the same number of electrons that are gained by Q1, as is the case here. And also, that is equals to the number of electrons that are transferred between these two materials, Q1 and Q2. Now, the follow-up question says, what charge was transferred? Now, the transfer obviously occurred between Q1 and Q2. Now, we also need to realize, as we've already mentioned, that the net charge remains constant. We still have a Q net of negative 3 nanocoulombs, okay? So the net charge is still the same, but the charge has now been equally distributed. So it says what charge was transferred. Now we're actually talking about the change in charge. It could be for Q1. Let's see, we know that change in science is actually equals to final minus initial charge. So the final charge is actually the new charge, right? In this case, the new charge, if we consider Q1, that is negative 1.5 nanocoulombs minus the initial one, which was actually plus 2 nanocoulombs, okay? Plus 2, okay? So in this case, this gives us negative 3.5 nanocoulombs. So charge 1 became more negative by negative 3.9 coulombs. In other words, the change in its charge was by magnitude negative 3.5 nanocoulombs. This was the gain. Now let's look at the change for Q2. Okay, still we're saying Q final, which is our Q new, minus the initial charge before they were brought into contact. Now the final is negative 1.5, which is the same as the final charge for Q1. Okay, minus the initial one was actually negative 5, right? So it's negative 5 nanocoulombs. So if you simplify that, it will give you negative 1.5 plus 5, which gives you actually positive 3.5 nanocoulombs. So delta Q2 is equals to positive 3.5 nanocoulombs. What does that mean? it means this one lost or it became more positive. And when you compare the change of charge of Q1 versus that of Q2 is of the same magnitude, just that one became more negative by gaining while the other one became more positive by losing, right? And then the other question says how many electrons were transferred. Now we want the number of electrons. This brings us to our, the main concept in as far as the quantization of charge. So when these two materials are actually brought into contact, what are we saying? We are saying the Q2, because it has got excess electrons, a certain whole number of electrons are actually transferred from Q2 to Q1, as was the case here. So we know that the principle says that every charge in the universe is a scalar multiple of the charge of a single electron, right? So this E is actually the elementary charge which is given in this case. So every electron has got that charge. So this principle, what it says to us, every charge that exists is actually in multiples of this number. So this is a constant which is the charge of a single electron. So if we can talk about Q1 for argument's sake, the number of electrons that Q1 actually gained. So if we would say to us, what's the new charge for Q1? That new charge is negative 1,5, okay, times 10 exponent negative 9. Why are we doing that? Because the elementary charge is in coulombs, while the charge of Q1 is in nanocoulombs, okay? So take note of that. So we want the number of electrons, so this is multiplied by negative 1,6 times 10 exponent negative 19, right? So if we want to find the number of electrons that were transferred, we'll make that the subject, okay? So if that's the case, then we'll get negative 1,5 times 10 exponent negative 9 divided by negative 1,6 times 10 exponent negative 19, right? So we can then go to our calculator. What is also important is that the number of electrons transferred cannot be negative, okay? So it's a positive or an integer number of electrons. We can have 10 electrons for argument's sake, but we cannot have minus 10. So when I do that division, the signs must actually be the same. So if we go to our calculator, we would actually get to a point where we say, okay, that's the division there, which is negative, take note of the negative that we used, negative 1,5 times 10 exponent negative 9. We divide that by negative 1,6, okay, multiplied by 10 exponent negative 19, right? So that's the calculation there. So how many electrons? That's a very big number. This is like 1, 2, 3, 4, 5, 6, 7, 8, 9. 9,375, right? 9, okay. If we can just go back quickly to that, 9,375 times 10. We need to go back because we want to write it in simple scientific notation there. So we've got how many zeros here? 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's times 10 exponent positive 9 electrons. So this does not have a unit because it's just the number of electrons. So when you do the same calculation based on the number of electrons lost by Q2, you'd actually get the same because the number of electrons lost is equals to number of electrons gained, right? So that, having said that, it takes us to, the summary as an overview, okay? We recognize and appreciate that all matter consists of atoms, okay, which has got the same number of positive provided it's neutral, okay? And then charge cannot be destroyed or created. This leads us to the principle of conservation of charge, which tells us that the net charge in a closed system remains constant. And it's only the electrons that are transferred when there is contact during any physical process, as explained by the law of conservation of energy. And all electrons have got the same charge, which is a constant, negative 1,6 times 10 exponent negative 19 coulombs. So this is a physical constant. Having said that, I think there's quite a lot we've managed to discuss during the course of today's session, but the main thing is about conservation of charge, how point charges interact with each other, and ultimately the fact that charge is actually quantized. Having said that, I think we've reached the end of our session. From myself, Tem Mangube is cheers and bye-bye for now.